Please, Pega.
Thank you
12
very
minutes,
much.
please.
I'll try to, I was asked, and I don't want to deprive you of coffee, so let's go. Situation with refrigerants is, in my mind, following. Ozone layer issues had eliminated many old good refrigerants, 12, 22, 502. Now, global warming will eventually eliminate some serious and reasonable replacements, 134A, 410A. What left is HFOs, that what is left on the surface that we see immediately, and sometimes mixed with other refrigerants, and of course natural refrigerants were always around. It is a question whether we want to use them or not. Toxicity was, in my mind, never compromised, but it looks like that mild flammability may become acceptable. Seriously, and maybe with some fun, but it's always mixed, I see two ways to handle refrigerant issues today. One is the approach by chemical engineers, and the other one is by mechanical engineers. I see that excellent chemical engineers are always trying to find either molecules, either single component refrigerants, or mixtures to satisfy a drop-in replacement option so that mechanical engineers don't need to work hard. I must admit they have been so good and they have been always able to provide whatever mechanical engineers needed. So not to work and just to go the way it is. Mechanical engineers like to build a system or have to build a system around refrigerant, and that's what some are trying, typically natural in that case. So what are the outcomes? I think chemical engineers' approach typically end up in a cost-effective approach, and that's why cost-effective solution, and that's why it is always kind of better accepted. Sometimes some people say unknown future because after one problem like ODP comes another GWP, and what will come next? Now, mechanical engineering selection is maybe long-term more promising, but near-term much more complex and expensive, and of course requires better understanding of the system, how to build the heat exchangers and whatnot. Now, in a current situation, after several ways of elimination, it's hard to find the good molecules. So even sometimes it is difficult to find good mixtures. So what we are seeing today is that HFO will become a constituent of most of the mixtures that will be around. And of course, we see a lot of pressures from natural refrigerants. This is a list of some of HFOs, and I have here highlighted the three of them that you hear mostly about. There are others that you may not have heard, but they are considered or not considered. Now, of course, we are mostly familiar with 1234YF or ZEE. Not that much of ZEZ, but anyway, I gave you here them to see as well. Now, these mixtures, of course, why do people make mixtures? Because there are no single component fluids that will go and replace something that is existing where we have existing machinery. Now, even that is becoming, as I said, a little bit more difficult to make, especially if you want to have a non-azeotropic mixture. So if you want to have an azeotropic mixture, if you want to go with the glides, it is relatively simpler, but even that is becoming kind of questionable. What are natural refrigerant options? Don't take me wrong, but I think only these three have potential to become some mainstream option in some, or ammonia already is. Ammonia, hydrocarbons, and carbon dioxide. All others that I'm listing here will always exist, as everything will exist, but in some niche applications. And they will stay for whatever applications they need to be. Just in a few words about ammonia. This is the only natural refrigerant that was continuously in use. Not really appropriated for populated areas when charge is significant, and as Didier Coulomb had said, charge reduction is one of the extremely important elements to maybe expand the use of ammonia. We have been working in '96. This is the first a prototype of air-cooled chiller with 18 grams per kilowatt and 50 kilowatt level. So that was, and I'm very glad that after a few years we have been asked to help, and this is one of Micom's chillers, air-cooled ammonia chiller, 35 kilowatts with a hermetic compressor. And I'm aware that in Italy there is another one recently, low-charge ammonia system. Now, hydrocarbons are definitely the lowest cost alternative. Almost drop-in replacement for 22 is 290, and for 12, 134A, and you can see in those. Now, flammability brings also charge reduction to the higher level, and 50 or 150 grams. I'm aware of the lowest one, 48, which was in public domain, that we have done for 1 kilowatt bottle cooler, which worked very nicely. Now, carbon dioxide is very old refrigerant, same as ammonia, and it was originally abandoned because of high pressures and bulkiness. Now, microchannel heat exchangers and other advancements in technology have brought this up again, and you see, nevertheless, it is assumed to be a low efficient refrigerant, and that's why I will spend maybe a few slides to kind of tell you what I think about that particular issue. And I will start with this chart, which is really the result of a long-term work that we have been doing for SAE, Society of Automotive Engineers, where we have been comparing various options. And this is 134A and CO2. The best was found at that time with 134A, and the best for CO2. Here you see COP as a function of ambient condition. And for the same, this chart is made for the same capacity of same size, same airflow rate, the same capacity. You see here two types of lines. Solid lines which are for higher speeds of compressor, like on the road, and these dotted are for idling, like in the city. So you see red and green are lines that represent 134A and CO2. We have came to, it is always well known that at higher temperature CO2 is less efficient than 134A. Nevertheless, where is that and how that looks like? For this type of systems, for automotive systems, this is something that was accepted by everybody in SAE, because that was done under auspices of SAE CRP. At 35 degrees C, our systems had the same efficiency, and when the compressor was running at 2,000 RPM. At something around 1,000 RPM, that equality of the efficiency is around 25 degrees C. So if you want to go to higher, you can go with CO2, but efficiency will be lower. Capacity will pick up, and efficiency will pick up at lower ambient temperatures. Now, let's say just something about COP. What does it mean? Why is efficiency so important? And there is a lot of misunderstanding about, in my mind, about efficiency of these systems, because that's used as a very strong argument. When we look into COP, we very often use that word, or efficiency, sometimes for cycles when we compare refrigerants, and when we compare systems, we add components. And then in application, we always need to add effect of operation. It means non-uniformity of velocity profile, difficulties in differences between lab performance and the real performance. So cycle analysis use terminology and tools of thermodynamics, and it looks into refrigerants only. Now, it works with the thermodynamics properties of fluid, and then you use like second law analysis, but it ignores realities of heat exchangers and compressor design. It ignores heat transfer, pressure drop, local sinks, and all of that. It is attractive because it is simple and clean, but it just appears to be unbiased because it doesn't give us the entire picture of what is important. It is excellent to evaluate option, but that's just the first step. And I'm always trying to say, go to the entire system. Because in Carnot's cycle, this is a Carnot cycle reminder for you, and I will not give you a test at all in 12 minutes presentation after that. So you see here, this is work needed, and this is to achieve something, and this is evaporation capacity. All fluids are equal because this is how it looks like. Nevertheless, the moment when we start to work with the real systems, we need to go to the dry suction to the compressor. We want to use not expander, but we want to use some small valve, cheap, inexpensive valve. Then fluids are not equal, they begin to differentiate. And that's where we need to look into thermophysical properties, not only thermodynamic properties, and the job of comparing different options becomes way more difficult. And I will make it even more difficult for you, even that is simple. If, for instance, these are the temperatures of heat source and heat sink, this black would be Rankine cycle with infinitely sized heat exchangers, which don't exist ever. Now, if we start to have airflow over condenser, and this is certain glide that is imposed by the airflow rate, and this here is the glide in the evaporator to remove, to take that heat and load it to the system, then you see that this black cycle becomes that blue. So temperatures start to go apart and COP efficiency start to go down. But what is the most important, the difference between this black line and this blue line, or this black line and this blue line, is a function of thermophysical properties. It is function of a heat exchanger. So it is very difficult, and it is wrong to use only thermodynamic analysis to compare refrigerants. You need to, if you want to give a meaningful answer, you need to take this into account. Why is this important? And I have said this here already. You can read it. But this is the point. Good selection can totally change initial expectations. Everybody accepted when you go and look into CO2 cycle, you get 60% efficiency of, let's say, 134A. But when you make a system and you make a good heat exchanger, then you see things way differently. How different it looks like, it is shown in these two, and I will show you two slides. In TS, in a pH diagram, 134A, ammonia, propane, and CO2. They are vastly different, even thermodynamically. In other words, you need to treat them in a nice way and to give them real opportunity if you want to do something meaningful with them. If you want to kill them, then you just drop them in the system and then you are done. We cannot get anything better, but if you really want to give it a fair trial, you need to understand, like everything in life, when you treat somebody with respect, you can get something in return. So this is pH diagram, and so this is, I'm coming to the end to conclusions. I'm saying here that CO2, for instance, is very different than 134A, ammonia, or 290. It has to be treated as such, and it is possible, but different way to achieve higher COPs. And I'm here stating 2 or 3 more things. And in a conclusion, this is what I would say. There was no time when only one refrigerant was universal. There are so many applications that one refrigerant can serve, and I believe it will stay that way. I believe that natural fluids like CO2, ammonia will expand their applications and will be more and more common. But there will be always many synthetic refrigerants, HFOs or mixtures or whatnot, because there are always applications which will be difficult, more difficult for natural refrigerants. When treated with understanding, as I said, each of them can do a good job. And these are main remaining tasks. Charge reduction, better materials, extremely low charge, safety, reduce expansion losses, improve heat exchangers. How to overcome initial cost is always a problem. This is nothing new. And engineers will still, both chemical and mechanical, will still need to show their ingenuity to find the best option for expanding and different applications. I hope I did not go too much beyond 15 minutes or so. Thank you.
Thank you very much, Pega. Sì, a proposito del condizionamento delle automobili, Sapete forse che le industrie maggiori tedesche hanno rifiutato l'1234YF e stanno pensando al CO2. E sono molto contento poi di sentire anche da Pega l'importanza dello scambio termico nel stabilire l'efficienza di una macchina frigorifera, ma direi non solo lo scambio termico, ma associato con le perdite di carico, perché guardare solo i coefficienti di scambio termico a parità di condizioni non è assolutamente sufficiente. Vi invito a approfittare della presenza di Pega Hrnjak qui, perché tutti lo tirano per la giacca in tutti i convegni del mondo, è molto difficile averlo a disposizione, è a vostra disposizione per domande, commenti. Chi vuole cominciare? Mi sembra impossibile che nessuno abbia curiosità, commenti o domande a Pega Hrnjak. Prego, vedo Dottor Schendre.
Thank you. Excellent. I think you gave a good perspective of practical dimension of the things. Because many people get emotionally involved in only the thermodynamic properties and give only one-sided view. My question to you is, have you done, your university or if it exists anywhere else, taking into consideration all the aspects, that is a refrigerant cycle, system design, operational issues, a comparison of two refrigerants or more than two refrigerants, and is it available somewhere where people can take that as a case study?
Thank you. Yes, I've done many research projects of that nature. And there are many papers that are doing exactly that. Maybe some of them are hidden in the number. Sometimes the problem is that the conclusion is hidden in the sea of various reports and the papers. So there are few, and I will be very glad to provide to you and others direct references where to go. Nevertheless, I think, yes, that is the most difficult, to find one which will summarize all of that, but I have several of them to point you to. We'll be glad to. We'll talk.
Prego.
Thank you very much for all the speakers. It's been very informative. Pego, could you please comment on the viability of CO2 in mobile air conditioning? And because there's been claims that it's not as efficient as HFC 134A in high ambient temperatures.
Wow, that is a very difficult question with many layers. I have been involved in that work probably last 18 years since very beginning, and very fortunately the comparison of various refrigerants, 134A and CO2 was in particular done. It was done through SAE cooperative research project. There have been many other refrigerants afterwards, and as you know, industry had chosen 1234YF to be replacement and, of 134A and not CO2. What we have done is our objective was to show what could be done in technical sense. That means what are the efficiencies, what are the capacities, and what is the behavior at high ambience. No question about that. At high ambient conditions, CO2 has less capacity and has lower COP. Nevertheless, you can design it to have the same capacity, to design it to have a higher COP at ambient temperatures of, let's say, 55, 60 degrees C. It is difficult. I would say, if I may interpret that the selection of 1234YF didn't come because 1234YF was a better performer than CO2. It was seen as the most logical choice in terms of reliability and the cost. You know what is happening today, so I should try to kind of not go into that direction. What we have been working on was, and what we have been showing is how you can improve the performance, if you want to improve the performance of each of the systems to reach the higher performance levels. And I had in some publications shown that how over the years we have been able to improve efficiency for more than 50–60% from where we used to be by just presenting a better way or demonstrating the better way to organize the system and heat exchangers. And that was true not only for CO2, but that was true also for 134A and YF. In other words, I could say that the efficiencies are pretty much wash, that very high ambient temperatures are not the best for CO2, lower ambient temperatures are better for CO2. Overall, LCCP analysis is favoring in a modest climate CO2 because more hours being spent at lower ambient conditions. I don't know whether I'm answering directly to your question.
Thank you, Pega. I
Sure.
think